Very good morning. Today we are going to discuss about the topic of analysis of clocked sequential circuit. We learned what we mean by sequential circuit. First, initially we did a combinational circuit. Then we discussed about the sequential circuit. Then we used a clocked sequential circuit that we are going to analyze today. So how we are going to analyze the clock? Suppose one sequential circuit will be given. Very well. The diagram indicates it's an with memory part, right? So in specific, it was given it as a clocked sequential circuit. So you can see the diagram. I mean, the first page diagram, we had a combinational circuit. What is the example for combinational logic circuit? It's nothing but a simple half adder, full adder, half subadder, full subadder that comes on a combinational logic circuit, which doesn't have a memory part, right? When it comes to a sequential circuit, along with combinational circuit, we are going to include this memory part. Okay. Here, this memory will be activated with the help of some clock signal. Hence, it is named as a clocked sequential circuit. So, the need for memory is that we are going to have a 1-bit storage that we are using as a flip-flop, right? So, actually, we are using flip-flop for this sequential circuit. So, we need to get the previous inputs and get and past feedbacks from this. Okay, for that, we are using a flip-flops here. Okay, let us analyze how this clocked sequential circuit will be. So one diagram was given, one logic diagram was given. So for this diagram, we are going to analyze for the given circuit, draw the state table as well as state diagram. So one diagram was given, it will be of input X, as well as two flip-flops were used. So two flip-flops. So two flip-flops were used. That is first flip-flop. We are using a TA flip-flop as well as TB flip-flop. The output will be of QA and the complement or conjugate is we can note it down as QA bar. So Q write in different color, hence can able to understand. Okay, now we are getting. So QA bar is a complement and QB bar is the complement. But in our circuit, we are not using this conjugate part. That is a complement of the outputs. Hence, we no need to bother about this. You know very well this is an AND gate, right? Here the output is nothing but an output of first flip flop along with the output of second flip flop, that is given as y is equal to, can write here y is equal to, it's an AND gate, right? So a dot b, we are using an AND gate over there. Y is equal to ab, or in some books it can be written as here it was mentioned output, right? So qa into qb, both are right. I am considering it's for ab. In some books it will be considered as an qa into qb. Okay, now let us analyze the inputs part. So for TB, what are the inputs? So one AND gate was connected. One of the input to the AND gate is A. That is our, you can consider this is an QA. The another input is from DirectX. So for TB, you can write here this is X into QA. That was the input to the second flip flop. Right. Now comes to the first flip flop, TA. So X is directly connected to the input of the first flip flop. Now can I write the state equation as, so in step 1 I am going to write the state equations as, so comes to here, T is equal to, from the given diagram can write T as X, then so TB is equal to Q into XA. The second input is TB is equal to X into QA. Then output Y is equal to A dot B. Okay, I will use the same notation, QA into QB. So as the first step, first we have written the given expressions, right? Okay, now the step 2. Step 2 is we are going to write a state table over here. So state table, So output is QA. So using two flip-flops as well as the inputs, right? So I'm writing present state, then the input, that is X. Okay, present state, input, and then we're going to write the next state. So we are using T flip-flops, right? So TA, then TB, then the next state. Next state will be represented as, if this is QA QB, this will be of X. Then automatically this next state will be of QA plus QB plus, and then the output Y, right? So for this I'm writing the possible combination. So 0 0 and my input is 0, 0 0 and my input is 1. Next 0 1, at that time when my input is 0, my input at 1. Next combination is 1 0, so input is 0. Next 1 1, other combination 0. At last it is 1 1, all ones, right? This TA can be this TA and as well as TB, there are the inputs, flip-flops. So this can be get with the help of this expression. So whatever value TS is actually is equal to X, right? So whatever in X, I'm going to write simply X. So 0 1 0 1 0 1. Okay. Next TB is equal to X into QA. So I have to multiply this. I will write in mark in some other color. So next I'm going to multiply this with QA along with X. So 0 0 0 0 1 0 0 0 0 0 into 1 0 1 0 0 1 1 1 0 1 1 not 1, right? Then this next state. So how you are going to write this next state? With the help of this characteristic table of, we are using an T flip-flops, right? So first you write the characteristic table of T flip-flop. So characteristic table of T flip-flop. So for this, how you are going to write? So Qn, then T, then the next state Qn plus 1. This is 0 0 0. This you know, right? You have to read this characteristic table. 0 1 1 1 0 1 1 1 is 0. Okay. So now from this characteristic table, we are going to get this QA plus as well as QB plus. So for that, we need to compare. I'll mention that in a different color again. We'll mark in red color. Okay. So for that, I have to compare this Qn with TA. If 0 0, then it is 0. So 0 1. So look at this, 0 1 means it is 1, right? So 0 0 0 0 1 1 1 0 1 0 1 0 1 is 1. In the similar way, I will write all the things 1 0 1 0. Then for QB plus, so QB plus I have to refer this 0 with this TB. Okay, 0 0 0 0 1 1 1 0 1 1 1 0 0 0 0. Just a minute. So 0 0 0. Next 0 0. Sorry, this is 0, right? So 0 0 0. Next one. This is 1. So this is 1 0 0 1 1 0 1 1 0. So I'm checking this QB along with this TB in order to get this the next state. Okay. Similarly for output QA into QB, so I have to multiply the present state. So 0 0. I have to multiply this with z, right? So only the last two values will get 1, right? So 0, 0, 0, 0, 1, 1. This was the state table. So with the help of this characteristic table, we are going to obtain this next state. Right? In discussing sequence detector problem, using the help of excitation table, we got inputs, right? So keep in mind, this was the difference between characteristic table as well as the excitation table. The characteristic table will give your present, will compare your present state along with the inputs to get the next state. Whereas in excitation table, by comparing present state with next state, you will get the inputs. Okay, this was the main difference. Okay, thus we obtained this state table here. Next, I'm going to consider for step 3 as I'm going to assign some states. Step 3, so I'm assigning S0 as 0 0, S1 as 0 1, S2 as 1 0, S3 as 1 1. Right? Now I'm going to step 4 to draw a state diagram. Okay, now we are going to draw the state diagram with the help of the state table we obtained. So after assigning the state assignment, I'm drawing first S0 state. So 0 0. Okay, that is 0 0. So 0 0 2. The next state is 0 0. When my input is 0 and output is also 0. It is when my input is 0, output is also 0. Right. Now comes to the second part. So when my present input is 0, when I'm giving 1 as input, it moves to the 1 0 state. So 1 0 state is actually S2, right? So I'm writing for S2. When S0 is moved to S2 state, when my input is 1 but output is 0. When my input is 1, output is 0. Right? Now third line. So when this is 0 1, 0 1 means it is S1 state, right? So S1 state 2, it was written at the same state, S1 only. So 0 1 to 0 1. When my input is 0, output is also 0. I'm drawing S1 anywhere. S1. When my input is 0, output is also 0. So hence it was written at the same state. Input is 0. My input is 0, output is 0. Let's come back to the fourth line. So again S1 S1 2, it is S3. S3 is 1 1. So it moves to S3 state. S1 to S3. When S1 to S3, when my input is 1, output is 0. Input is 1, output is 0. Right? Next 1 0. 1 0 is S2. S2 to 1 0. When my input is 0, output is 0. S2 to written at the same state. When my input is 0, output is also 0. Next from S2 to 0 1. 0 1 is 1 0. Sorry, 0 1 is S1. So S2 to S1. S2 to S1. When 1 is given as input, at the time output is 0. That was thing, right? When 1 is given, output is 0. Next comes to 1 1. 1 1 is S3 state. S3 to S3. It was remain at the same state. No input is 0, but output is 1. S3 to, so S3 to S3, S3 to S3, when my input is 0, but my output is 1. Okay. Now come to here 1 1, that is S3 to 0 0, input is 1, output is 1. So S3 to S0, S3 to S0, right? S3 to S0, 1 is given as input and output is also 1 1, S3 to S0. In other words, this can also be drawn by replacing S0 with the help of the state assignments. Right? You can write this also, right? 0 0, 1 0, this is 0 1, this is 1 1, and when my input is 0, written at the same state, the output is also 0. So 1 0, this was written when my input is 0, output is also 0. Moves to the next state, 1 is given as input, 0 as output. That was written at the same state, when my input is 0, the output is also 0. It moves to 1 1, my input is 1, output is 0. It was written at the same state, 0 as 1, 0 as input, 1 as output. Then 1 1 to 0 0 state, input is 1, output is 1. This is also right. Both you can prefer either by this way or this way. So both were right. So that's implementing the state diagram. Okay. So the questions may be asked in two different ways. One case, maybe we are going to design this logic diagram with the help of the state table as well as the state diagram, and then we are going to implement the logic diagram. Or in some cases, that is what we discussed now. Some circuit, that is a logic diagram, will be given. From that, we are going to analyze what is the inputs, what is the outputs, and then we are going to analyze the state table, that is the present state, input, and the next state as well as the output. In order to write this next state, you need to know this characteristic table. Without knowing this characteristic table as well as excitation table, you cannot able to design a circuit part in digital system design. Okay. So now, after obtaining the state table, I am assigning the state assignment values S0, S1, S2 as well as S3, and then the state diagram was implemented with the preceding state table. Okay. So any doubts, we'll try to solve more problems. If you have queries, you can come and ask me. You can use any flip-flops. Here it was mentioned T flip-flops in circuit. In logic diagram itself, they mentioned it is an T flip-flop. The T flip-flop was given, right? So it is an, you can see here the clock was applied to both the flip-flops simultaneously, hence it is a clocked sequential circuit. So instead of this, they may use JK over there. We'll have some circuits. Okay. I think that we discussed in class. So JK flip-flop was there. So for that case, you have to write JA, JB, KA, KB. So you have to write, suppose if in the during class we discussed those things, those problems. I think we used two JK flip-flops, JA, KA, JB, KB. For that you have to write the next state. Then you're going to write the output Y. So in order to get the next state, you have to know the characteristic table of JK flip-flop, right? In this problem, we are having only T flip-flop, so hence we are using this T flip-flop. So what are flip-flops? Here it is somewhat difficult. Here the flip-flop was specified, right? So you have to know this characteristic table. If nothing was given, I mean like a sequential vector problem, if nothing was given, then you can go for any flip-flops design. So either by JK or by D or by T, whatever you want, you can able to design. Okay. So hence it is essential you people has to study the characteristic table of all the flip-flops as well as the excitation table. Without knowing this, you cannot able to perform well. Okay, if you had queries, you come and ask me. Thank you.